So now we're going to get into the good stuff. Vectors in space. Now, space is also referred to as R3 because it's the coming together of an x-axis, a y-axis, and a z-axis, all of which represent real numbers. Therefore, it's the real number line a total of 3 times. So, x, y, and z. Suppose that you have an initial point and a terminal point. We'll refer to this as the point P, and we'll call it x1, y1, z1. And we have a point Q over here that we will refer to as x2, y2, and z2. If I were to connect the point P to the point Q and give it a direction, we officially have a vector in space. So with that in mind, the vector PQ would be defined very similarly to how we saw vectors in 2 dimensions. We would take the terminal point minus the initial point, so x2 minus x1. For the y component, this would be y2 minus y1. And now we're going to have a z component as well. That is the 3 part of R3, so 3 different components. Now additionally, there is another way that we can express some special vectors. In 2 dimensions, we had the I and the j notation. I represented a unit vector in the x direction. J represents a unit vector in the y direction. Both of those stay the same, but they need that necessary 3rd component as well. It is the vector k that is going to represent the unit vector in the z direction. So anytime you have a vector that's of the form, say, xyz, this could also be expressed as a combination of these 3 vectors, calling this x times I plus y times j plus z times k. So both of these notations work out okay, and that's your intro to vectors in R3. Now, everything that we can do with multiple vectors in 2 dimensions, we can do essentially the same thing with vectors that are in 3 dimensions. So let's cover what a couple of those things would be. First thing we'll do is define a couple of vectors. This notation differs slightly with what you see from the book, but I like referring to each of the components as its own bit. So we're going to refer to the vector v as having components v1 for the first component, v2 for the second, v3 for the third. And we're going to do something similar for a vector that we'll refer to as w. So the operations that we have vector addition. If I want to add the 2 vectors together, if I want to take v1, comma, v2, comma, v3 and add it to the vector w1, comma, w2, comma, w3, this is once again adding component-wise. So add the first components together, add the second components together, and add the third components together. I suppose the notation that I should have used in this first line here would be vector v plus vector w to make it look kind of official. We also have scalar multiplication. Scalar multiplication. If I take a scalar like c and I multiply by the vector v, that c is going to distribute through to all 3 of the components. The reason I typically use c for a scalar is because scalars are constants. Constant, c. Sometimes I feel like I teach spelling more than I teach math, but that's neither here nor there. Combinations of vector addition and scalar multiplication are referred to as linear combinations, and they get studied pretty extensively in a linear algebra course. Additionally, if we wanted to do vector subtraction, subtraction is simply saying multiply one of the vectors by -1 and then add them together, but we'll go ahead and toss it in here anyway. So if I wanted to do v minus w, this would be v1 minus w1, v2 minus w2, and v3 minus w3. The significance of vector subtraction is that this is what you would get by connecting the terminal point of one vector to the terminal point of another vector, assuming that they share an initial vector. We have magnitude. The notation that we'll use for magnitude, we'll go with the double absolute value brackets, and that'll refer to the magnitude of a vector, and it works the exact same way as it did in 2 dimensions. It's based off of the distance formula. Take the first component, square it. Take the second component, square it. Take the third component, square it, add them all together, and then take a square root. As far as unit vectors in given directions, we can define a unit vector in the direction of a given vector. So direction of v, that would be the vector v divided by the magnitude of v. And if we wanted to go for the direction of vector w, this would be the vector w divided by the magnitude of w. So typically with those you'll see a lot of radicals. Simplify the radicals as much as possible, and when you're dealing with the fractions, be sure to reduce those as well. We'll do some examples in the next video.